This is weekly formative assessment number 4. As per usual, you should do it first and then watch it once you've used your 2 attempts. So let's go ahead. I'm doing this blind, so I could get stuff wrong. Let's see, what problems do we have? We have 12 minutes, so maybe like 6 questions. Atwood machine is shown, and there's mass string. Mass is completely frictionless, and M2 is greater than M1, and it falls a distance h. So we got to find the acceleration. Now, there's a really quick way to do it where you treat the thing as a whole, as like a whole system. But I think the way Mr. Bose wants us to do it is treat them as separate systems. So you say, hey, for M1, right? Or I guess M2 is larger than M1. So start with M2. So F net equals MA. M2 times A, right? That's mass 2 times acceleration. That's the F net. Is going to equal, the sum of the forces. So M2G, right? Fg minus Ft. I'll just say it's T. And then here we have, if we use F net over F net equals Ma, here we get M1 times A. It's going to equal T minus M2G, right? I change the signs because I'm essentially looking at the magnitude, right? So if I change the signs, right, I will, if I do M2G minus T, it will be a negative acceleration, right? Because the acceleration is upward, and you're saying downward is positive. But I don't want that. I want magnitude, so I flip the signs. And then I can actually substitute in T over here, right? So M1A minus plus M1G equals T. I sub that in. I get M2A is going to equal M2G minus M1A minus M2G, because I distribute the negative, and I get M2A plus M1A equals M2G minus M1G, and I think you'll see I have A is equal to G times M2 minus M1 over M2 plus M1, where I factor out the A over here, and then I divide by M1 plus M2. So I can confidently select that. Then I'm going to, okay, so this is motion with net force, motion without. And so with no net force, there's going to be no acceleration. And that looks like it's going to be graph 1 and graph 4, right? Graph 1, because the slope is constant, so the velocity is not changing. And graph 4, because it shows the velocity is not changing over time. Constant net force, that's going to be our graph 5. That looks graph 2 and graph 5. Graph 2, because the slope of velocity is acceleration and it's constant. Graph 5, because it's showing that acceleration is constant throughout time. And then I can say graph 3 and graph 5. Oh, I forgot to put graph 5 over here. Graph 3 is the only one with a variable net force where the acceleration is actually changing over time. Do I have 6 questions? Oh, I have, okay, 6, okay. So block M is placed into equilibrium, and we want to find the smallest amount of force that will allow this to occur. So, and what's the coefficient of static friction? So at the smallest, so let's draw an FBD, right, of the block. So if we have the block, I hope my pencil didn't die. That would be my Apple pen. Well, not really an Apple pencil. I have the F min here, and then there's the normal force that's, kind of counteracting that. There's going to be the weight force, mg, and there's going to be the upward frictional force that keeps the whole thing up. Friction is the thing that keeps this thing up. At the minimum force, friction is basically acting at its strongest, right? Any less than F min, the thing will fall. So friction's acting at a maximum. So force friction, at maximum, it's Fn times mu, right? So Fn times mu is going to equal mg when the forces are still balanced, right? Fn, well, that's just equal to F min, right? Equal mg. So I get mu is going to equal mg over F min. And you can actually show that these 3 options that I'm selecting right now are actually incorrect just by units. So we're going to have this block being pulled, and there's this frictional force, and there's going to be a normal force, and there's going to be Fg, right? And we want to see which of the following is true. Well, you got to know P is greater than F, right? Because P is going to have a component upward and a component to the right. So if friction is opposing that, P has to be at least greater than friction, right? Not necessarily equal because there's a component upward, but at least greater. Not at the least. That's not an appropriate word of that word. Just it has to be greater. And we actually know Fg is going to be greater than force normal, right? Because the deal is the y. So if there's no pull force, Fg is equal to Fn, right? But if there's going to be a component of the pull force that's upward, well, in the y direction, the net force has to be balanced. So if you have more force opposing Fg, your Fn actually gets smaller, right? Because this plus the upward force will actually equal weight, right? If you get rid of that pull force, Fn goes up because it's the only thing keeping this block up. So I think everything else would be false just based off what I would say, what I just said. So giant wheel diameter 40 fitted with a cage and person with mass m stands on it. So the force exerted by the man on the platform is equal to his weight when the cage is at position X as shown. So, what is going to be the direction and magnitude? Hopefully, the direction is going to be downward because we need a radial net force, and the radius of the circle would kind of be pointing down, I guess. Radius doesn't have a direction. But hopefully you get what I mean. It needs to be center seeking, so the force would be pointing down, right, into the center. If you draw your FBD, there's going to be the mg, but Fn is going to point like so, right? It's up at the top. It's pushing him down. So the total net force is going to be 2 mg, right? Because it's Fn, which is equal to the weight, plus mg, so it's going to be 2 mg. And then we have a pendulum here, so makes an angle theta, released at A, travels through B, and then stops at C. So the magnitude of the tension in the cord at the instant it is released. So this is actually, if you actually draw this out, there's going to be Ft, which is going to, and then we have Fg. Really, Ft is actually balanced by this component Fg. You can call this kind of FGR and then Fg, I guess, parallel. And the reason I know the reason I've split my force into these components is because at point A, there is no centripetal acceleration, right? There's no centripetal acceleration. So radially, there can't be any net force. So those forces are balanced. And the reason I know there's no centripetal acceleration, I kind of glossed over that, is because centripetal acceleration is equal to v squared over r. So if v is equal to 0, a is equal to 0. At that instant, and as it builds speed, it's going to kind of, there's going to be a radial force. So because of this, I can kind of say, hey, if this angle, if this angle right here is theta, that means this angle right here is theta. So I know the tension is going to equal, Fg cosine theta. And then I can get, Fg cosine theta. So let's see if that works. We're going to press submit. All right, 6 points. Cool. Thank you for watching.